As we continue on in Chapter 7, Reactions and Aqueous Solutions, today we're going to be looking at reactions that form water, acids and bases. Arrhenius acid and bases. There was a Swedish chemist named Arrhenius, Svante Arrhenius, and he proposed this idea of what a definition of a strong acid and a strong base should be. And that's what we'll kind of stick with in this lecture. So a strong acid is one which almost all of it is going to completely dissociate into water to form an H plus ion and its anion. So for example, if we take a look here at hydrochloric acid, if we put hydrochloric acid in water and it becomes aqueous, we don't really have hydrochloric acid together as a molecule. It goes into its ionic form, into H plus ions, which is aqueous, and chloride ions, which are aqueous. The same thing with nitric acid. It breaks up into hydrogen ions and nitrate ions. And we see that with sulfuric acid, it has two hydrogen ions, and the first one will come off completely and leave it with a hydrogen sulfate ion and hydrogen ions in solution. This is just showing us that the strong acids behave as strong electrolytes because they completely dissociate in water, and you end up with positive ions and negative ions. A strong base is a metal hydroxide that is completely soluble in water and giving separate hydroxide ions and cations. And the most notable examples of this are going to be sodium hydroxide. When you put it in water, it's going to break up into Na plus and OH minus, and potassium hydroxide does the same thing. Notice just like the acids, they will break up into their ions. The products of the reaction of a strong acid and a strong base are always water and a salt. And that means that there's always a net ionic equation that's the same for all acid-base reactions. A reaction of H plus and OH minus is called an acid-base reaction, where the H plus is our acidic ion and our OH minus is our basic ion. Let's take a look at how we come up with a net ionic reaction that looks like this one. Okay, let's start with writing out a general reaction for an acid and a base. So we're going to take hydrochloric acid, which is aqueous, and we're going to add sodium hydroxide to it, which is also aqueous. And when we do the double date switch, we're going to put hydrogen with the hydroxide, making liquid water. So it's H2O liquid, plus our sodium and our chlorine together. So our sodium ion and our chloride ion. And we know that those are going to be aqueous because of our solubility rules. So if we were to go ahead and take this and split it up like we did with the precipitation reaction, we would have H plus aqueous plus Cl minus aqueous. Oops, I should have made sure I was balanced. So there's 2 hydrogen, 2, 1, 1. So we're balanced. Okay. Break these up, continue to break these up into ions, like so. And on the other side, instead of breaking up water, because we're going to treat it like we did that solid with the precipitation reaction, it's liquid, it's not aqueous, so it stays in molecular form. And then we continue to go ahead and break up any aqueous substances that we have. And just like with the precipitation reactions, if we got rid of our spectator ions, you would notice that what we have going on is exactly what they said the net ionic equation was for every strong acid-base reaction, which is this. So an acid-base reaction starts with a strong acid, a strong base. You end up with water, liquid water, and this is called a salt. So this is an ionic compound formed from this reaction. This salt happens to be common table salt, which is sodium chloride, but it could be other salts as well, because it's an ionic compound that is formed from a metal and a non-metal. We're going to call that a salt, and it's a result of this acid-base reaction. So here's our net ionic equation for every strong acid-base reaction. This is one of those you don't really have to work out because it's commonplace and it's something you expect to get every single time. So that's what where that came from in the lecture. Let's look at a summary of strong acids and strong bases. The common strong acids are hydrochloric, nitric, and sulfuric acid. A strong acid is a substance by definition that completely dissociates or ionizes in water to form its hydrogen ion and its anions. And a strong base is a metal hydroxide compound that's very soluble in water and dissociates into hydrogen ions and the cation as well. The net ionic equation for the acid-base reaction is always the same. It shows the product of water. And in the reaction of a strong acid and a strong base, one product is always water, the other is always an ionic compound we call a salt, which remains dissolved in the water. This salt can be obtained as a solid by evaporating the water from it. The reaction of H plus and OH minus are often called an acid-base reaction. H plus is the acidic ion and OH minus is the basic ion. Look at a concept check. The net ionic equation for the reaction of nitric acid and lithium hydroxide is which of these? And again, after I just showed you the one example of what a net ionic equation looks like for an acid-base reaction, you go up here and you notice that this is nitric acid, which is a strong acid, lithium hydroxide, which is a soluble base. So if I do the double date switch, get rid of the spectator ions, this is a classic net ionic equation for an acid-base reaction. That's going to conclude this lecture for reactions that form water, which are reactions dealing with acids and bases being put together. In order to be really good at this, you need to practice with doing some more net ionic equations, not just with acids and bases, but with other compounds as well, forming precipitates, and also to memorize the groups of strong acids and strong bases that your book gives you.